Hello students. Continuing our unit of moment of inertia of different bodies with different shapes, we are now to study the moment of inertia of uniform disk about an axis passing through its center and perpendicular to the plane of the disk, as we did in the case of ring. That if we have a disk, if disk is lying in xy plane, then its axis is passing through z axis. So considering a disk which is lying in xy plane such that origin is at center of the disk, we have to find the moment of inertia about z-axis. So one thing is clear, that we are again choosing, according to our algorithm, plane polar coordinate system. So we are to work with r and theta, and since we have to find the moment of inertia about z-axis, therefore the n cap in this case will be equal to k cap. Now we consider that moment of that m is the mass of the disk, and let r be the radius of the disk, and also we assume that sigma is the surface mass density. Sigma is surface mass density of a ring. So since it is mass density, so sigma will be equal to mass over area. So area of a disk is pi r square and mass is m. So pi r square. Also, following our second step, that we have to identify a small mass element. So I identify a small mass element somewhere here. Okay, this is dm, which is at distance r from the center and making an angle theta with the x-axis, and this is having surface area ds. So therefore, following our second part, we have to study now dm. So since surface mass density is mass upon area, so if we are considering is this small part, so it will be dm over ds. Therefore dm is equal to sigma ds. Now we have the value of sigma as m over pi r square. We will substitute this value of sigma m over pi r square in this equation. Hence we get the equation as dm is equal to m over pi r square ds. Now our next purpose is to find ds. So area element in the case of a disk or in two dimensions, as from mechanics we know that it is given as r d theta into dr. So it, in a simple way, I can write it as r dr d theta. I substitute this value of ds in this equation. Therefore my dm is equal to m over pi r square r dr d theta. Remembering my third step in the algorithm, that I have to identify di. So di is given as dm n cap cross r absolute square. So now my next purpose is to identify r. As we have seen the figure that r is making angle theta with x-axis, and therefore r can be written as xi cap plus yj cap, or it can be written as r cos theta I cap plus r sine theta j cap. This is bit different from the case we did in the case of ring, because in the case of ring, if I consider the case of the ring, it was like this. I had to consider r up till here on the surface of the ring because it was hollow from inside. I am repeating, it was hollow from inside, but the disc is not hollow from inside. So r can lie anywhere. It can be here, it can be here, it can be here, it can be here. So r can also vary, and its value is from 0 to capital R, that is radius of the disc. I hope it is clear. I am repeating again that in the case of the ring, since ring is hollow from inside, so r has to be either at this point or this point, because this is also hollow, so r has to be at this point. But in the case of disc, since disc is not hollow, it is solid from inside, so this small r can vary from this point to this point, means it can vary from 0 to r. So therefore I have not considered capital R from here. I have considered small r. Substituting the value of n cap that we considered is equal to k cap and r here, and also substituting the value of dm, I get di as k cap cross r cos theta I cap plus r sin theta j cap absolute square, and the value of dm is m over pi r square r dr d theta. Again solving it, I get it as r cos theta k cross I is j cap. So I will be initially solving this equation, and this part k cross r cos theta I cap plus r sin theta j cap, it's square, so it comes out to be r cos theta j cap minus r sin theta I cap, and it's square. As we did in the previous lecture, we can find its value as n cap cross r. It comes out to be, it's absolute and square, under root of r square cos square theta plus r square sin square theta, and it's square. So n cap cross r, it comes out to be square, it comes out to be r square. So di, again substituting this value in the value of di, as discussed the value of di in the previous page. Here I will substitute the value here, so my result will be di is equal to m over pi r square small r square r dr d theta. So di is equal to m over pi r square r cube dr d theta. Now remembering one important point, that here if I have to calculate I need to integrate di. Looking this equation closely, we can see that here are two variables, dr and d theta. The variation of r is from 0 to capital R, as I discussed earlier, and variation of theta is from 0 to 2 pi. Because it is a disk, so angle can vary from 0 to 2 pi. Therefore, I is equal to capital M is constant, capital R, which is radius of the disk, is also constant, so it can be taken out of the bracket, out of the integration. Hence, I can further write it as m over pi r square 0 to r 0 to 2 pi r cube dr d theta. Solving further, I get it as I is equal to m over pi r square, 0 to capital R cube dr, 0 to 2 pi d theta. Further I get I is equal to m over pi r square. So its integration is r raised to power 4 by 4 and limit is from 0 to r, and integration of d theta is theta, its limit is from 0 to 2 pi. I is equal to m over pi r square into, if I substitute the limits, r raised to power 4 by 4 and lower limit of r is 0, it will be 0, so r raised to power 4 by 4. Similarly, limit of theta is 2 pi. This pi cancels out, r square cancels out, this 2 cancels out, and hence my answer is m r square by 2. So this is the value of moment of inertia of a disk about an axis passing through its center but perpendicular to its plane. That's all for today's lecture.